Ion exchange chromatography is used to separate charged molecules like proteins, amino acids, nucleotides, and nucleic acids. The stationary phase is a solid charged resin packed inside the column. This resin can be positively charged, which makes this anion exchange chromatography, and it can be negatively charged, which makes it a cation exchange chromatography. Meanwhile, the mobile phase is a liquid buffer that carries the sample through the column. So what happens is that when the sample enters the column, molecules with no charge and same charge as the resin move straight through. But molecules with the opposite charge to the resin bind to the surface, and the strength of binding depends on how strong the charge interaction is. Weakly charged molecules bind loosely and come out earlier. Strongly charged molecules bind tightly and come out later. Now we need to break the ionic interaction between the sample and the resin so the bound molecules can come out. We can do this by two methods. First, increase the salt concentration. Salt ions compete with the bound molecules for the charge sites on the resin. As salt concentration increases, bound molecules are displaced and come out of the column. Second, change the pH, which can alter the charge on the molecule itself. If the molecule loses its charge, it can no longer bind and it elutes. For proteins, this becomes extremely powerful. Every protein has something called an isoelectric point. If the pH is below its pi, the protein carries a positive charge. If the pH is above its pi, the protein carries a negative charge. By carefully choosing the pH and salt gradient, we can separate proteins that differ by even a single charge unit. That level of precision is why ion exchange chromatography is one of the most widely used techniques in protein purification, antibody production, enzyme isolation, and clinical diagnostics. Here, separation is not about boiling point. It is not about size. It is purely about electrical attraction.